theorem says that if you take a point in the moduli space of principally polarized abelian varieties, and if you take an ordinary point, take all of its Hecke orbit, then what you get is a dense subset of the moduli space. And this at least should seem plausible because there is no a priori p-adic constraints, like they have to lie in certain Newton polygon strata. Okay. And then there's a similar statement for the Hilbert modular varieties that we discussed on Wednesday. It says the similar thing if you take a point in a Hilbert modular variety. Here I'm using F. You remember that in the Hilbert modular variety case, in general, we were using a product of totally real number fields. But since such a modular variety is actually a product of the corresponding ones, each one corresponds to a totally real field. So the statement can be stated in equivalent form just for one single totally real number field, which is stated here. Okay? You take a point which is ordinary in the sense that the underlying abelian variety is ordinary. You look at its prime to p Hecke orbit. This time, the underlying group is an SL2 with respect to that totally real field. Again, the statement is that you get a dense subset. Okay? And I would like to break this down into a number of digestible steps so that we can sort of match them with the progress. They are written in the notes, except that there are a few things we have done before, so the numbering wouldn't be the same as in the notes. Okay. So I guess here, I'll explain what they mean. So the step one is that for every point z in such a orbit, y0, which is smooth and ordinary. I'll explain what that means. So if one takes a formal completion, I'll just write this as ZF over Z, then this is equal to a product of the factors that we discussed previously. I should say that I omit the L and L prime and M. I'll just write it as F as for simplicity. Then with a P, Z, P in a subset as Z, which is contained in the set of all places of the number field F above P. So let me record the definitions here. So definitions or notations. So sigma Fp, remember that F is a totally real number field. And then this is the set of all places P in F, finite places, P, such that P divides P in OF. All places of the totally real number field F above P. Okay? And what this says, and you also recall that last time we said that for any point, for any closed point of the moduli space, if I complete it at the closed point, then it decomposes into a product. You remember that the reason being that the underlying Barsati-Tate group decomposes according to the places above P. So that we have a decomposition P in sigma Fp, which I just denote by an index Z here. Okay. So this was done the last time. Call for you. And that's because we have a decomposition the completion of the total real number field above P. Okay. So that's the first step. The first step says that if we take a point here, we complete, if that point is ordinary, then we will get information that it's the completion of the completion of the Zariski closure of the Hecke orbit is very simple. It's just a product of finite number of copies of these vectors. Okay, that's the first step. The second step is that this SZ is a finite subset of this finite set, right? For every Z, you have such a thing. And then the second step says that this dependence is locally constant. So SZ depends only on the irreducible component, or that's the same as connected component of the regular and smooth locus of this Hecke, the closure of the Hecke orbit in which this point Z lies. So it's a local constancy statement. Okay. 3 is that, remember, there's a statement, well, that Franz explained that in using the stratification due to Ekida-Oort, there is some consequence of the Ekida-Oort stratification, which implies that this point, the Zariski closure of every Hecke orbit contains a supersingular point. Using that, we'll see that this leads to a contradiction. Okay. That's the first 3 steps. These 3 steps will prove the density of Hecke orbits, a contradiction to 2. 2, if SZ is not equal to the whole thing. We want to show that it's the whole thing. If it's the whole thing, then this Zariski closure has the right dimension, meaning that a priori, so every irreducible, well, some irreducible component has the dimension equal to that of the moduli space. But we know that the moduli, sorry. Yes, thank you. That's much better. Implies that SZ is equal to FP. And we know that the moduli space is reducible if some component of this Zariski closure has the correct dimension, then it has to be the whole thing. And there's only one component after all. Okay? So that's the first 3 steps. That will prove theorem 2. And the 4th step is that we will use theorem 2 to show that there exists a point, what's my notation here, x1 in the Zariski closure of this given Hecke orbit. And that point is ordinary and such that if I write this point, if every point, so I have write it A1 as a polarization as a level structure, right? P bar. And I'll show that you can locate a very special kind of point in as follows, that this underlying abelian variety has the form that it's isogenous to the self-product, the product of the number of copies of a elliptic curve, and E1 is ordinary, and it's defined over FP bar. That's the elliptic curve. Okay. So this is somehow the only use that we make of from theorem 2. But this is a crucial one. Okay. 5 is that using the linearization techniques at this very special point, we see that the local stabilizer principle that we discussed before, plus the local rigidity implies a theorem. So now let's go to them in order, linear order here. So 1. Okay. So let's see what we want to say, know about 1. So it says that here, if I take the Kazarisi closure of the Hecke orbit in a Hilbert modular varieties, now it has to be one of a finite number of possibilities, very, very special ones. How do we do that? So first, maybe I should say 0, because to do 1, we need to recall the Tate coordinates in this special case. So I recall for you Tate coordinates. What does it say? It says in the case of A0, I have used A0. Let me not use A0. I have used 1. I think I don't have much choices in the term in these numbers. I have to go to 2. So A2 is ordinary. Let's say abelian variety over at P bar. And I recall for you that we have explained, we have seen that, so we'll look upon deformation space over FP bar. Okay. And we saw that it's a formal torus. What is it? Well, we know that it has the following form. You can take the p-adic Tate module of, it's A2 here, you take the P divisible group, take the maximal état quotient of that, okay, and we hum it to, so this is hum over ZP. What do we hum it to? We hum it to the formal completion of A2, which is the formal torus. Okay? And this, by duality, is the same as hum ZP. TP of A2 P infinity, that's the same thing as before, tensored over ZP with the p-adic Tate module of the transpose of T2, taking its Bersati-Tate group, maximal état quotient. And here we just have the formal torus. That's the statement. This follows immediately from duality because this is, so the formal completion of A2 is just hum this into that. Okay. So now let's sort of change A2. So in the notation here, we have a B0. This thing has multiplication by the random integers of this totally real number field. Okay. What happens if we impose this endomorphism? So for B2, I guess iota 2, so the multiplication, lambda 2. So what happens then is, you go through the notes. There's something I didn't have time to explain in the talk, but it's written down explicitly in the notes. So what the condition of imposing certain endomorphism should be. And you work that out, and what you see immediately is that now in my writing, I omit the L and L plus because they don't, so it's understood. So I complete that at this point, which I called Y0. What is that? That is, if you go through that, it's almost the same thing. It can't be the same thing. This is B2 now, P infinity, eta, tensored with TP of B2 transpose. Maybe I should put transpose here. P infinity, eta, GM, hat. And you ask what's happening. They look the same. And what's happening, the difference is that here, because the Abelian variety admits endomorphisms by the ring of integers of this totally real number field. So this condition becomes exactly that you should sort of impose these conditions. And that becomes exactly the condition of passing to the tensor product. Okay. Now some comments on these things are in order. So what do we know about these p-adic tape modules? Well, if you think about the dimension of B2 is equal to the dimension of the totally real number field, and then the maximal, therefore this maximal état quotient has height exactly equal to that of the dimension of the totally real number field. So the consequence of that is that this is a free OF tensor ZP module of rank. What can that be? Just one, because this is already a free ZP module of rank equal to the dimension of F. And both of these are. Okay. So when you take such two free modules of rank 1 tensored over this thing itself, you'll again get a free module over that ring of rank 1. So what this means abstractly is that this is a formal torus and then has endomorphism by OF tensor ZP. And non-canonically, it's isomorphic to this thing. So this is non-canonically isomorphic to a number of copies. How many? As many as the dimension of F. And here. And if you don't mind, you can choose non-canonical isomorphism. I just think about it as a sort of very not tensor product. That's what that is. Now, oops, I think I made a mistake. Probably should, oops, put down both points. Okay, now we are ready to prove at least step 1. Why? You remember that we have this local stabilizer principle. What it says is, in this situation, is that if we take the unitary group attached to the following semi-simple algebra with involution, what's that? That's endomorphism algebra of was it B2? I'm sorry, I wrote B2, but it should be B0. All of the B2s there should be B0 because I didn't have a B2. I'm not sure why I had a B2 there. So please. B0 tensor with Q and linear. And then we have the involution attached to any of the polarization there. They are all the same. I'll just write ZP with a grain of salt. So this defines, so there's an open subgroup of the unitary group attached to it. Okay. I'll leave it to you to work out what this unitary group is. In another example, we'll work it out in more detail. But all you need to know for at present is to admit is that this is quite sizable. In fact, the dimension of this group is equal to exactly the dimension of the totally real number field. So I'll give you a hint. So what is this? So this is a totally imaginary quadratic extension of which is split above every prime P divide P lying above P. So you should be able to figure out what this is. Okay. So this is essentially. So all I'm saying is that this is non-canonical. Well, there are two choices that are equal to OF tensor ZP. It's the local units. But in fact, it's the local units of this imaginary quadratic extension that give it a name capital K. Then it's the local units of K which has relative norm 1. It's the norm 1 subgroup operating on it. Now, so this operates and stabilizes what? It stabilizes ZF of Y0 hat of Z for each such Z, which is smooth and ordinary. This is the local stabilizer principle. The reason being that the Zariski closure of the Hecke orbit has to be stable under all Hecke correspondences. Now, if you look at the stabilizer inside the Hecke correspondences, now that stability of that this is stable under a part of the Hecke correspondences translates into exactly that this subscheme as a subscheme of MF, of the completion of the Hilbert modular variety is stable under the Hecke action. This is a formal torus that we just saw. We just explained what this is, right? This is that formal torus over there. Now I have this subgroup operating on it. Now apply the local rigidity. The local rigidity is a pretty strong statement. So all it requires is that this action is not completely trivial. It doesn't contain so totally trivial subquotient. And this certainly it doesn't. You can check that very easily. Okay. So the conclusion is that this is a formal subtorus of that Certé local torus. But it's not just an arbitrary subtorus. There are lots of subtori, but this is a subtorus. So this here, so ZF Y0, completed as Z, is a formal subtorus of the Certé torus, but with one more property that's stable under this action of this local stabilizer subgroup, which we know we completely understand this via linear algebra. Okay. And then what can it be? You have the this formal subtorus. It has a character group or co-character group, but this co-character group is stable under this action. You don't have much choice. This module can only be the product of finite number of factors. Okay. So, and that implies the statement 1. Okay. Is this clear so far? Sorry? What? Smooth? Smooth? The small z. Oh, z. No, it's every z. For every z. So this is as the statement in ZFX0, which is ordinary and smooth. I should also remark, maybe this is a good chance, let's remark that there are lots of smooth points. For instance, I'll just say that ZFX0 or ZFY0 is smooth at Y0. Okay. Why? I'll leave this to you as an exercise, but I'll indicate enough about the proof orally. Why is it? Well, this is a Zariski closure that therefore it's reduced. Okay? Now being reduced, what does that mean? Well, one implication is that there exists a dense open subset such that the dense open subset is smoothed over Fp bar. But it's a dense open subset, and by the very definition, that dense open subset must contain Y0. And that's the end of the proof. So this is what I just described is an analog of the fact that if you have a group operating on an algebraic group operating on an algebraic variety, then every orbit is smooth. The proof is that there is some point that in the orbit that's smooth, and therefore by homogeneity every point is smooth. And you translate that into the present situation, you get a smoothness. There are lots of smooth points. Okay, so we have done one. Okay. What about two? So we have a pointwise statement that for every smooth ordinary point, we have defined this finite subset. It's a particular finite subset of the set of all primes above P. Okay. And all we need to know is that for some point, this SZ is the whole thing. Because if you know that, then at that point, this Darcy closure of the Hacker orbit it's smooth, it's formally smooth, therefore smooth at the point, and has dimension equal to that of the moduli space. And the moduli space, you know, is irreducible. Therefore, it's the whole thing. Okay, so with that in mind, so now here the 2 is a relatively weak statement, which most of us will just naively take for granted. Right? For every point, you attach a finite subset. Now you say, well, this has to be, locally constant somehow. Okay. So I just have to supply you a reason. Okay. So 2. What's the reason? You use the globalization that we discussed the last time. So the globalization that we discussed the last time, I'll remind you what that was. So last time we had this MF. First, we always know that their MF is diagonally embedded into the product of 2 copies of this thing. And therefore, we can consider, so to speak, the family of tangent cones, or so it's called delta of MF. Okay. And we said that the last time that this is product. So I just index it by P. So each one is a part of this tangent cone. This is smooth, so each one of these is some scheme formally smooth over Fp. The fiber product, this is a fiber product over MF, is the whole thing. At every point, it reduces to the decomposition of the formal completion that we explained. That's the globalization. So this decomposition is not arbitrary. It comes with this. Now I'll leave it to convince yourself that if you think about this, then the local constancy statement follows. This is an exercise in algebraic geometry that you can easily do. Okay. So that's the end of 2. What about 3? 3 says that, well, okay, so we know that it's locally constant. That's expected. So what's the big deal? Now we want to know that, well, how do we conclude that this is not possible? So suppose that, so at every point, let's say, for the sake of argument, there a priori may be a finite number of irreducible components. But let's just assume a priori, all of them, they're constant, and everywhere it's just a fixed, proper subset of this finite set, which is the set of all places above P. Right? What can go wrong? Well, intuitively you say, well, this is nonsense. I mean, you can't have something, this almost look like that you have a algebraic decomposition of your moduli space and so on. This, of course, it doesn't happen. The point is that we have to give some suitable reason that that can be regarded as a proof that it really doesn't happen. Okay, so the point is that the Ekeda-Orr stratification, using that as Franz explained in his lecture, that there exists, now let me appoint, let me use S. I'm afraid of using numbers because I'm sure to get the numbers wrong, so Zi. So in this Zariski closure, such that, which is super singular, let's just say. Okay, so that's explained. So the super singular means that that point itself, the underlying point corresponds to a super singular abelian variety. Well, plus endomorphism plus level structure, and plus polarizations. Okay, now you have this constant. It lies in the closure. So you think about, you take that closure. What you see is then that the F completed at S, then, I should be a little careful. So I'll say that suppose, okay, this is fine. Okay, so suppose, I look at that point. Now, so this S, I have a finite number of components. Now, all of them not equal to this. Okay. Now, if I take the closure, there's an exercise in algebraic geometry, which I'll let you do, which says that this point, so this is contained in the product of M, this is over S, P, for P over a proper subset of sigma F. Okay, so this is sort of exercise. There are various ways to do this, which I'll just assert it here. Okay, so now what's wrong with this? So this, by the way, is just by taking closure. Okay, now what's wrong with this? The problem with this that this is a serious problem, because you have some factor P. So let's say a P1 is omitted. That's a serious problem, because in deformation theory, what that means is that when you deform along this end, you don't change the factor. So I write, so I have B, so I have this S corresponds to sort of B, B sub S, lambda iota sub S, lambda sub S, eta sub S. Okay. So BS, P infinity, that's super singular, but as anything, it decomposes into a product of Rosati-Tate groups. This is universal. So it's true at every point. Now this deformation space, this local completion, being contained in that means that when you look upon the deformed p-divisible group along this factor, so the factor Bs P sub 1 infinity, which is containing here, does not deform. doesn't deform at all. Okay? Now, why is this a problem? We know that when you go to the closure here, well, it's generally at the you evaluate it at the generic point of this formal scheme. You should get an ordinary abelian variety. Okay. But here you see that if you omit any factor, that factor stays constant. It doesn't deform. And therefore, this is a contradiction. This contradicts the fact that I'll just say that the universal, this is a universal abelian variety, and then over the generic point of that is ordinary. That's a contradiction because of a factor which has slope 1/2 and 1/2. This just can't happen. Okay, so we have proved 3. And so now we declare, modulo a few details that I didn't carry out, that we have proved theorem 2. Okay? Is there any question that I should clarify? So the idea I should stress is it's quite simple. So the reason that this would work really is a coincidence. The reason that this kind of proof will work is that the Hilbert modular variety is in some sense very small. And therefore, so the key is that, so using, in general, if you try to apply this kind of localization technique using the action of the local stabilizer subgroup locally, in general, you will never get into a possibility that a priori you just know that there are a finite number of possibilities. It just simply doesn't happen in general. In general, you have lots of possibilities. But here, just because that this modular variety is small, this small is reflected group theoretically in effect, when we heard about Shimura varieties, that corresponds to a Shimura variety. Every Shimura variety has a group. And that group is either GL2 or SL2. Let's take SL2. It's SL2 over F. Its Q rank is 1. And this is sort of it's a small modular variety. And therefore, we have only a finite number of choices, and that allows us to do this kind of argument. And therefore, so this kind of argument, if we try to do it directly on the Ziegel modular variety, it just doesn't fly. I mean, I hope there is a general argument, but so far I haven't found it. And if anyone has any idea, I'd really love to hear that. Okay. So please remind me, I'll try to keep that board. If I ever attempt to erase that board, please stop me immediately. Okay. So now, where should I go? I go to number 4. Okay. So this number 4 is where what Franz advertised already. This is we can call the Hilbert trick. And this is sort of one of the this is the crucial weakness of this argument, of the entire argument, and also the crucial weakness of so far of the methods available for studying tachysymmetries. Okay. And because this depends on a coincidence in life, so to speak. The coincidence is, as Franz explained, that if you take the Ziegel modular variety, this is in some sense, some people will say the mother of all Shimura varieties, or the prototype of them. But this is not the most general Shimura modular variety you have. It has this property that through every point, every closed point, so let's say even points defined over FP bar, you can find a modular subvariety. In fact, it's the reduction of a Shimura variety passing through that given point, and that subvariety has positive dimension. There are few modular varieties have this property. So Ziegel modular variety is one of them. More generally, for instance, all modular varieties of PEL type C has this property. But generally, it's a non-flyer. There's too much to expect. And that's where, but we are here, we're in one of these special situations, and this has this special property, and we'll exploit that. So I'll state the property that I'm going to use. So the property that I'm going to use, and then I'll give some words to explain it, at least to explain it to a point that this is believable. So I have F, L plus. So I'll say that, so given a point, so here we have given the point x0 in AG1n, and it's ordinary, right? Okay. The assertion is that we can find a diagram with the, so x0 is ordinary with the properties explained. FG bar, thank you. So the claim is that I'll be able to find a suitable Hilbert modular variety, but here, in general, we will need a finite number, not just one, a finite number of totally real fields. There may be even repetitions, for instance. And some m is as before, m is bigger than or equal to 3. It's prime to p, and so on. And this is, and then we can find another thing. And then a diagram like this. So this is, only look at the ordinary part. And so this goes to the ordinary part. I call this G and that F. What are the properties that I want? I want that G is finite flat, and F is finite. Okay. And this map F is Hecke equivariant. What does that mean? Well, this means, among other things, that here I have Hecke correspondences. I have natural Hecke correspondences coming from the group, I'll say SL2, defined by E using prime to P finality. I think we explained that before. Although I explained it only on this level. But here is a finite flat thing, there is a natural one. I'll try to indicate that at the very end if I have time. And so finite flat, F is flat, and now I have one more crucial property that we know lots more than what properties about this diagram that I'm going to describe, but there's a crucial property. It's that for every z, let's say, did I use z? For every z here, I'll have the property that here I have gz. So I write gz as, what did I write here? Gz, I guess I write somehow bz iota z because one needs to use some intelligible notation. So if I have a point z here, it gives me a point gz here. It corresponds to a Boolean variety with real endomorphism by E and polarization and so on. And then I have fz here. I have az, lambda z, eta z. Okay. The property is that the weak property we need is that bz is isogynous to az for every z. Roughly, let me first indicate very roughly to make this even plausible. So what's happening here? If we have So we started with, oh, I'm sorry, there's one more thing I didn't say. So, and also, so that's one thing. And then there is another thing, is that there exists a point, point y0 in M E L plus to L plus and A F P bar, such that f of y0 equals x0. Okay. So roughly what this says is this. I would like to understand the Hecker orbit on here. Okay. So the Hecker orbit, so I have a point I'm giving myself. So suppose that I have given myself an abelian variety A0, that's explained in the notation up there, and with principal polarization and a level structure, right? Now I would like to only understand, so this is somehow, it's something that's difficult to understand. Or difficult to understand in the sense that it's difficult to get information about the Zariski closure of its Hecker orbit. That turned out to be difficult in general. So I'll say, well, I'll be less ambitious. I'll only look at a part of this Hecker orbit and hope that that part of Hecker orbit will produce something whose Zariski closure is understandable. Okay. What do? I say, well, you remember from Fran's talk that if so let me say, we pull a board here. So the idea is that I'll just take a small portion. Maybe I should. I just take, so the Fran's talk, we know that this abelian variety A0 being defined over the algebraic closure Fp bar of Fp. It's defined over some finite field. So this has sufficiently many complex multiplication. Okay. And this also comes with a Rosati involution. Then in Fran's talk, Franz explained that here you can find a product of totally real number field such that, so the rank or the dimension of EQ is equal to the dimension of the abelian variety, which is or half of the largest possible dimension, but with the and being a totally real number field and fixed by the Rosati involution. So this is if you want to have a product of totally real number field contained in it, this is the highest dimension you can get to. And Franz explained that this actually happens. You can always do this. So what this means is that if you modify the abelian variety A0 using some isogeny, you modify the polarization a little bit, then you will get an abelian variety with anamorphism by the ring of integers of OE. And then you quickly see that you get yourself some element, some point in the Hilbert modular variety. Now if you want to get back to, from that, you want to get back to the original one in a systematic way in families, you may need to trivialize, do a little bit of trivialization. You need to trivialize some level structure, namely you have to trivialize some finite torsion groups, both possibly prime to P and also possibly divisible by P, but by a bounded amount. So you trivialize that. What that means geometrically means that you go to a finite cover. In general, this finite cover may be problematic, but we are restricting to the ordinary locus, and that's a good part. So it's really finite. It's really finite flat. It's a pretty good cover. So, and then just geometrically, we see that there is a natural extension of Hecker correspondences. Now, because this map F is really defined geometrically, we see that this map is compatible with Hecker correspondences here and Hecker correspondences here. Okay? And moreover, this statement that we need, that if I have a point here, it corresponds to some abelian variety. Now these two, I said that, well, I look at the result of the abelian variety here in the Ziegel space and here in the Hilbert modular variety, that they're isomorphic, they're isogenous. Why? Because I'm just sort of going over and then and divide out by some certain isogeny construction. So by construction, these are true. Okay, this is the Hilbert trick. Okay, any questions so far? Oh, I should keep that. I think I'm in good shape. I was a little worried that I may not be able to finish. Now the only problem is to find, here this function. Sorry? Well, Hilbert, this is the Hilbert modular variety. This is a very special, this is a trick because this doesn't apply in general. So here this is a precise statement sort of which expand the remark that through every point over FP bar of the Ziegel modular variety, you can find a modular subvariety, which is quote unquote a Hilbert modular subvariety content which passes through that point. It's a big subvariety, big in the sense that the dimension is G. It's far from 0. The dimension is quite far from the dimension of the Ziegel modular variety, which is G times G plus 1 over 2. But its dimension is G. G is still not bad. Yeah, I guess semantically, but well, this is Grothendieck. We should honor Hilbert, the great man. Okay, so I think I should erase this so that we don't have any confusion. Okay, now we're down to 5. 5 says that the 5 sounds strange. So what does 5 mean? So here the point is, if you look at the Hilbert modular variety, like I say that there are lots of points that I can almost just pick randomly. This is a whole modular variety. What's a point I can pick? I pick E1, so it's an ordinary elliptic curve. I hope that you do. I've used E. I'm conscious about that. I've used E, but E1 is not a product of totally real number field. E1 is an elliptic curve. Okay? I pick one, and it's ordinary, and it's defined over FP bar. Then I have a point. I take E and make some copies of it through, and force that to have endomorphism by OE via this standard construction. This is, again, if you like. So an abstract way of saying this is that you think about E as a sheaf in either the FPPF or FPQC topology. And then as a sheaf, you tensor that sheaf with OE. And then you check very easily this is representable by an abelian variety, actually, and that's denoted by this. Non-canonically, you just take a basis, a Z basis of OE, and then you have a finite number of them. How many? In this case, G, right? Yes. Sorry? This is E1, thank you. This is just Z, thank you, that I was just blind. Okay. So this is a G dimension, you take this abstract, this is a G copies of this ordinary elliptic curve. But it has a real end. And then you can complete with the product polarization and so on. Polarization, natural action. and then choose level structure and so on. Okay, so that gives me a point. Now, this is difficult. I need to give a name. Naming something is always difficult. I guess I haven't. Let me be careful. I use y5. I don't think I have ever used 5. So I have a point in here. Now I know that I can lift it up. We know that by what we know from theorem 2, I know that the Zariski closure of the Hecke orbit on here surjects to the Zariski closure of the Hecke orbit here, which is everything. So I can find something here which maps to the Zariski closure of Hecke orbit here, which maps to the given point y5. And then here I have a y6 here, maybe z6. Here and here that lies above it, but z6 lies in the Zariski closure of the Hecke orbit above. This is y0. Okay. So the upshot is what? The upshot is that I can find a point, now let's say x5 equals a5, lambda 5, eta 5 in the Zariski closure of the Hecke orbit of the original point that we want to study, such that A5 is isogenously to G copies of that ordinary elliptic curve over Fp bar, right? I'll repeat the logic. The logic is that, so I know that here I have a point, here I have a point, I think that's denoted y0 here. So at point y0 here, the Hecke orbit of y0 maps to the Hecke orbit of x0. That's Hecke equivariance. Now the Hecke orbit, if I close this Hecke orbit of y0 here, that maps to the Hecke orbit here. This is finite and flat. Therefore, the Zariski closure of the Hecke orbit surjects to the Zariski closure of the Hecke orbit here. But here I have a very special point, meaning that here I can find some point mapping to the given point. Okay? So I have that. Now, what's good about it? So all of these, what this does is that it allows us to produce some point in the Zariski closure of the Hecke orbit x0 that we somehow have some information. That's all it does. I pick out a subset of Hecke orbit, not the whole thing, but there, because I understand Hecke correspondences a little better on any smaller Hilbert modular variety, so I have produced some point. Okay. Now I say that this is almost the end of the proof. So the last, I'll show you that from the linearization technique, so we linearize and use the local stabilizer principle, and the local rigidity will conclude the proof. Okay. So what do we know? Now let's look at this subvariety. Now I guess that's x5 now. Okay. What do we know about this? x5. Well, first, it's a formal subscheme over x5. So if you like, yeah, it's smooth. Okay, so this is very good. So this is, I think the image I'll call that, no, x5 is here. I guess this is y5. Oh, no, this is x5. I'm sorry, this is fine. This is x5. So this is a Serre Sear-Tate formal torus. All right? Now, what else do we know? This is stable under what we explained as H sub x5. That's the local stabilizer subgroup. How large is the local stabilizer subgroup? Well, you remember that the local stabilizer subgroup comes from E1 G copies. We look at its endomorphism tensored with Q, and then there's a polarization, therefore induces an involution. Now, what this is just G copies of OE1 tensor Q. But in Francis' talk, we have seen that this is what? This is a total, this is an imaginary quadratic field K, so split above P. And therefore, if I look at this point over, so this is an open subset in the unitary group attached to the endomorphism E1 tensor Q star 0, QP points. But this is something we understand now. So this splits so that this group is just GLG of QP. Okay, so that's GLG of QP. Now, so GLG of QP operates on this, the Sear-Tate torus. The Sear-Tate torus, this is hum of sim square of TP of, and it's containing here, we have a representation. We have the natural action of an open subgroup of this group operating on here. What's the representation? So this action comes from a representation of this general linear group on the set of character group, the set of formal characters of the Sear-Tate formal torus. It's the representation. By its very construction, it's the symmetric product, the second symmetric product of the standard representation. And that we know. We know some information. We know that that representation is absolutely irreducible. This is one of the fundamental representations of GLN or GLG. Okay? Now, I say we're done. I'll just say it orally, but apply the local stabilizer principle. We know it's stable. Now, by local rigidity, we know that we should get a formal subtorus. Now, this formal subtorus has the property that its formal character is stable. It's a subspace, sub-representation of this absolutely irreducible representation. What can that be? You know that it's not trivial. Has to be the whole thing by irreducibility. Therefore, you're done. It has to be the whole thing. So, QED. Thank you. Thank you for your attention.